Okay, this is section 9.3 for MAC1114. In this section, we're going to be talking about complex numbers, numbers that are in the form A plus BI. You've talked about that in your algebra classes, but now we're going to take these numbers. They're still going to be complex numbers, part real, part imaginary, and we're going to put them in polar form. And we're also going to put them in exponential form. I want you to synonymously think of the A as the X value and this as the Y value, because then you can relate some of the formulas that I'm going to talk about to formulas that you were given in a previous section. Okay, so in this first problem, all you're asked for is the conjugate. They just want to remind you what a conjugate is. And that is, all it takes for that is to switch the sign in front of the imaginary term. So the conjugate here would just be 8 minus 2i. Pretty simple, no work for that problem. Just remembering what a conjugate is. Okay, then in the complex plane, when you are graphing, this axis is where they plot the real numbers, and then along the y-axis is where they plot the imaginary numbers. Okay, so the x-axis is referred to as the real axis, and then the y-axis is referred to as the imaginary axis. Number 3, when a complex number, they call complex numbers z, just refer to them as z in this section and in the whole chapter. And in polar form, it looks like this. It has the modulus out front. That's called the modulus. It's really just the hypotenuse of the right triangles that you're going to be forming. And then the theta, you know what theta is. We've done a lot of work in this class figuring out theta from the reference angle. Okay, so then let's see, what do they want here? Right, a complex number. Yeah, they want to know if you know what the words are that talk about the non-negative number r. They're asking a question about that. Is called the modulus or magnitude. Magnitude means the length of. When you're in the vector section, it's called the magnitude, and it can also be called the modulus. And then the angle that you see right here, that also has a name. It's called the argument. So these are just vocabulary words, and that would be this choice right here. Okay, then you finally get your first complex number. This happens to be in rectangular form. As I said, you can think of this interchangeably as the A and the B value, which we typically call the real coefficient, and the imaginary coefficient, we typically call them A and B, but they can also be thought of as X and Y. The A value is X, the B value is Y. So when it's in this form, this is said to be in rectangular form, just to get you familiar with these things. Then the magnitude, which is also the modulus, is just if you're doing R, and you see that the A and the B value have been given as X and Y. It's just the real coefficient squared plus the coefficient of the imaginary squared and a square root. Okay, so that would be choice B. Okay, going to the next page. I haven't to do any calculations yet. This is number 5. Flatten this out a little bit so you can see it better. Okay, so plot the complex number. That's easy. Again, the numbers on the x-axis is where you plot the real portion, and the imaginary portion gets plotted along the y-axis. So you're going to 4 and then up to 4i, and you're in quadrant 1. Okay, then it says write the complex number in polar form. Select the correct choice and fill it in. So whenever you're going to write in polar form, then you need to be remembering what is the formula for the polar form of a complex number. So from the previous page where they stated the formula, Again, it is r times cosine of theta plus I times sine of theta. So all you're really looking for in order to get it in this form is theta and r. Okay, r, they also just gave you a formula for that on the previous page. It is the real portion squared plus the imaginary coefficient. No i's or anything here. So this would just be 16 plus 16, which is the same thing as 2 times 16, which is the same thing as taking the square root of 16 and bringing it on the outside of the radical, 4 square roots of 2. So that is your modulus or magnitude. So that's going to be part of the answer. The other thing you need in order to get it in full polar form is the theta. Now typically I would tell you to find the reference angle first and then the real theta, but you're in quad 1. See where the point is? It's all about where this point, the original point is. If it's in quad 1, that means the reference angle is the same as the actual and final theta, and therefore you can just jump right to the final theta. You're always going to find your thetas with the formula y over x, which is the same thing, is synonymous to b over a. The b value is the value that is right here, the one in front of the I term, and the a value is the real portion. Anyway, they are both the same, so it's 4 over 4, which is equal to 1. Okay, so you are trying to think about what angle is do we get what angle can you take the tan of that you would get a value of 1? Or you can think of it like this. You could go inverse of 1 is equal to theta. And when you're doing inverses that there's a restriction to be in here, quad 1 or quad 2. So the theta, I think a lot of you have this memorized, that when you're getting a 1, that is 45 degrees. They want your angles in radian form, so I'm going to state that as pi over 4. They're going to want all the angles in pi over form, radian form in this section. So I'm going to keep talking about them like that. Once you have your theta and your r value, you're ready to put it in polar form. They're also going to want you to put it in exponential form, but let's write polar form first. So first you want to find the formula that has cosine of theta without the I next to it, because the sine should always have the I next to it. Cosine term first, and then sine term in the back, and it is the imaginary portion of the complex number in polar form. Okay, so that one would be right here, part D, and out front you're just going to put your modulus, and then you're going to put your thetas here. So your theta turned out to be pi over 4. You're always going to be using the same theta for the cosine and the sine term. And that's it. Okay, then when you're in exponential form of a complex number, so you have this polar form that we just came up with. So we plotted it, we put it in polar form. And then there's also the exponential form of a complex number. It still has an I in it, an I term, otherwise it wouldn't be complex. But when you're in complex form, your complex number, they use the letter Z for all complex numbers, it looks like this. It's got the modulus multiplied by the number E, and the E has a power on it, and that power is I times theta. So the R value is going to be, in this case, 4 square roots of 2. We just calculated it over there, times E. And then this is like the coefficient of the I term. So let's see, what was our theta? Pi over 4. So pi over 4 times I, and probably looks a little better if you put it in the front, as we typically put coefficients. So if you were going to type that into MyMathLab, you would just go pi times I over 4. The I belongs in the top. That's it. That's everything for that problem, number 5. Okay, moving on to number 6. Okay, number 6. Again, you have a complex number, but this is in rectangular form. It's got an X and a Y, or what we would call an A and a B. Right on top of the, okay, so the A value, I'm going to write right on top of the stapler. The A value is the 10, and then the number in front of the I, that is your B value. Think of this as X and this is Y, so you can relate it to formulas you've been given in previous sections. So if you want to write this in polar form, again, you're going to need the R and you're going to need the theta. So just like the last problem, R is x squared plus y squared, or you could call it a squared plus b squared. Just take those numbers right off the complex number, the coefficients, which are 10 and negative 10 square roots of 3. And square each one. So I'm squaring the 10. I'm also squaring the negative 10 square roots of 3. This would give me 100. The negative 10 squared would be negative 10 times negative 10. That would be 100 times. And when you square the square root of 3, you just get a 3. So you have 100 plus 300 all happening underneath this radical as you try to get your R value. So square root of 400, that turns out to be 20. So there's your R, and then we're going to work to get theta. So this time we're not in quadrant 1. We are in, let's see, positive x, negative y. Positive x, negative y. 2 of the answers did get cut off because if there's 4 pictures, it always cuts it off when you print it. But this is the right answer anyway. And I think if you look at your answers in the answers that came with the packet, it's choice A, which makes sense because it's a positive x and a negative y. So it would be this one right here. Okay, but anyway, my point is that when you plot this point, it's not in quadrant 1. So in that case, when you're not in quadrant 1, as we were in the last problem, you're going to need to find the reference angle first using tan, just like we did in the last problem, and then find the angle that's associated with it, the real theta. And let's see, so we'll go y over x or b over a, so that would be the b value plays the role of the y. And the a value plays the role of the x. Okay, so b over a, the 10's cancel. You end up with negative square root of 3. Okay, and then you can think about what kind of reference angle is going to be happening there. You already know that you're in this quadrant right here, so you can go ahead and draw your picture as though you're in that quadrant. Maybe you want to write it with all these little, without all the little grid marks and the numbers and everything. Maybe just draw like a nice clean picture right in here. You know you're in here. Go ahead and close up that triangle and put these values on here. So the values that you're going to use are, you can think of this as negative square root of 3 over 1. So this would be the y value, this would be the x value. Would be the x value, and then this would be your hypotenuse. By the way, let's see. Oh no, that was in a previous problem. Never mind. So we put square root of 3 over 1. And so if you were trying to think, you know, what the reference angle is, what kind of special right triangle is, this is the one you should recognize as being the long leg. Therefore, this is 60 degrees, also known as pi over 3. But that's just your reference angle, what you're seeing right in there. So if this is your reference angle, then what is the real theta is where this hypotenuse is. Okay, so let's see. What do they want? Yes, okay. So we're going to think about this in thirds. Okay, so this is 1/3. So let's think about this in thirds. So 3/3. This would be 6/3. And then you want to figure out how far have I rotated to get right there. Okay, so when you rotate this far, let's say you were on your way to 6/3, but you stopped 1/3 before you got there. That would be 5 pi over 3. Okay, so that's your real theta. That we've done a lot of in Chapter 6 and Chapter 7 and Chapter 8. Not so much in Chapter 8, but a lot in the other chapters. And then it comes back, a lot of Chapter 6 comes back in this chapter where you're having to rotate around the circle and everything. So we're using that here, where we got the reference angle first and then we got the real theta. Now take this information, the r and the theta that you have, and now you're ready to put it in polar form as well as exponential form. So make sure you're picking the right mold here. It goes cosine theta plus I times sine of theta. So that would be right here again, cosine and I times sine. You want to make sure the I is the imaginary portion and it's always connected to sine. Well, that goes right here. You're going to put your modulus out front. You're going to put your 5 pi over 3 here. And you're going to use 5 pi over 3 here. You'll always be using the same theta for both of those. Then when you go to put it in exponential form, again, that formula is like this, that for any complex number, it is the r times e, and then as the power that's on the number e, I multiplied by theta. So in this case, that would be 20, and then e, and then I times theta. Your theta is this 5 pi over 3, so 5 pi over 3 as the power multiplied by I. That multiplier of I will always be in the numerator. So 5 pi times I over 3 for that power. And I know I kind of crunched it in. Here's a better view of it. A little bit bigger. On to the next problem. Okay, moving to number 7. Get another pencil. I'm wearing down the lead on this pencil. Okay, so plot the complex number again. Okay, this one's going to be 13 minus 13i. So it's like positive x, negative y. So 13 would be here, and then negative 13. Just line these up. And that's where it is in quad 4 again. And then you're going to need your r and your theta again in order to put this complex number in polar form. So we're going to go for polar form again, then we're going to go for exponential form again. There's a lot of repetitiveness here, but you need the practice. So here's r. Formula is x squared plus y squared, or you can call it a squared plus b squared. Okay, so this is 169, and then you could write it like this, only because you'd be breaking it down anyway just to do a partial square root. You had 2 of the 169s. There is a square root of this, as you can just see here, it's 13, so this comes out as a 13. And the 2 stays underneath. So that's your r value. And then the theta, find the reference angle first. And then you can find the real theta. So this is coming out -1. And so the reference angle associated with a negative value like this is 45 degrees, which is pi over 4. And then if you're in this quadrant right here, I'll just draw my picture here. I got plenty of room right here. And I'll put my right angle right there. The reference angle would be pi over 4. And then what we want to think about is what the real angle is associated with that reference angle. So let's think about this. We've been talking a lot in this class about how to count in fractions. This 1 pi location, if you were rotating around this as though it was a circle, this would be 1 pi, or also 4/4. This would be 8/4. And so if you were rotating like this, trying to make your way to where this hypotenuse is, which is where the real theta is, that would be called 7/4. Excuse the water that's being lapped up by my dog. He's very thirsty. That's probably going to go on for a while. Okay, so this is your reference angle right in here, and the reference angle allows you to get the real theta. So real theta, 7 pi over 4. Okay, then once you have the theta and you have your r value, you're all set to go with the polar form and the exponential form. Okay, so the z value, make sure you pick the right one. It should go cosine and then I times sine. That would be choice C here. Your r value was 13 square roots of 2, and your theta was 7 pi over 4. Okay, and they even tell you that use an angle that is greater than 0 but less than 2 pi. So they want you to give, a positive angle there. All right, so then number 8, let's go to number 8. Okay, so let's see, this time we're going to see that it says in the directions that you are rounding to 3 decimal places. It did not say that in number 7, nor did it say that in number 6. And it's because this is not going to be something where you have a familiar reference angle. It won't be a special right triangle. Therefore, you're going to have to use your calculator in order to get the reference angle and the theta. So first, let's see where this is. If you were going to plot this, you would have to go to -6 and then all the way up to 7i. So you're right there in that quadrant, and you can even do your work for the triangle out here because this is where the theta is going to be. Okay, anyway, since you are not in quadrant 1, you're going to have to find the reference angle first and then the true theta. Okay, so here we go. We're going to do the r value first because that's what will go out here, and that is just x squared plus y squared, or a squared plus b squared. So this is your a value, and this is your b value. You're squaring these two numbers. -6 squared is 36, 7 squared is 49, and when you add these up, you get 85. Okay, then when you go and try and find theta, you're going to do your reference angle first, which is the b value over the a value, or you can write it as y over x because b is the same thing as y and a is the same thing as x. B is the back value, a is the front value. Okay, so your y value is 7, or your b value, and your a value is -6. Okay, now if you want to get the angle for this, then this is, again, these are not values that you're familiar with. They don't belong to a special right triangle, so you're going to have to use your calculator. So you're going to go in your calculator. You know how you find angles. You go inverse of the value that you're working with here, 7/6 negative. You do the inverse and you'll find the reference angle. But because this point is not in quadrant 1, it's in quadrant 2, the reference angle will not be the true theta that you're going to be using in this answer or in this answer. So that'll be the step after that. So first let's figure out what this is. When you do inverse of this, you get, hold on, get my calculator running. Now you want this to be in radians because it says here, type any angle measures in radians. So make sure your calculator is in radians, and then you're going to call up your inverse of -7/6. So inverse tan, -7 divided by 6, close that up. Reference angle is positive, and I'm going to hold on to 4 numbers while working the problem point, 8622. I'm writing it in its positive form because reference angles are positive. So this is 8622. But then if you want this real theta, you have to think about it like you think about it when you're doing pi. You were rotating until you got right here and stopped. And if you want to know how far you've rotated, well, you were almost to 1 pi, which is 3.14, but you stopped this much short. So this number is something less than pi. And if you want to get a number less than pi, then you have to subtract. So it's that, and you're subtracting off the reference angle, 0.8622. Okay, so put that in your calculator, pi minus 0.8622. And you get, if you round to 3 decimal places as they requested, 2.279. And that's your real theta. Okay, so you see, the real theta is not the same thing as the reference angle if you're anywhere besides quadrant 1. So if you're here or here or here, you're going to have to go through the reference angle step and then finding the actual theta. Okay, once you get these things, then you're ready to give both of these answers. Okay, so let's find the one that's in the right format. It should start with cosine and end with sine, and that should have the I on it, which is this one. You're going to put your modulus out front, which in this problem is square root of 85. And then as far as the theta, it turned out to be 2.279. You use the same one for both of these, cosine and sine. Okay, that's the end of that problem. Just wanted to do one with a decimal for you. Okay, moving on to problem number 9. Okay, problem number 9. We are going backwards now. In all these problems, just so you'll understand, you're going back the other way. So you were given these problems in rectangular form. See, there's no r, no theta, and you were going into the r theta form. Oh, by the way, when I finished problem 8 here, I didn't put it in exponential form. I might as well give you that while I'm on this page. Did you see how the form that these are in? This is rectangular form. And now you're going to go back the other way. I'll give you the polar form on the next page, and you come back to this form. So anyway, to finish this answer, giving it in the exponential form, that's where you go r, the r value, times E, and then the power on the E is going to be I times theta. So I times theta, this is your theta, and then times your I. I have to give you that piece. Okay, so here, with these problems, it's already in polar form, and when it's in polar form, the R is found out there, and this is the theta. You can either look here or here because they're going to be the same. That's your R value. Okay, so when you're trying to go into this form, go into rectangular form, you want A plus, you want to get it back in that form. And that's how the previous three problems that I just did, that's how they started. So you're going back the other way. This is the same thing as X. This is the same thing as Y. And you were given all the way back in section 1, and it was in every section after that. The form, how do you get an X using an R and a theta? X is R cosine theta. So in this case, it would be the R value, which is 4, times the cosine of 5 pi over 3. And we can draw a little picture for that and then use it for both of these answers. Y is R times sine of theta. So we'll go grab the values right off of this picture, but this is 3/3, 4/3, 5/3, because 6/3 is right here. So by the time you stop at 5/3, that means you were 1/3 away from 6/3. So when you close up this triangle, that 1/3 that you see at the center, at the origin, that is 60 degrees. Therefore, this is the long leg. So square root of 3 is your long leg, and it is negative. Circle that so we don't lose it. This is your short leg, and this would be the hypotenuse. The hypotenuse is always double the short leg. Okay, so when you come back and finish these, the X and the Y, so that we can finally give this answer right here in rectangular form, all we're trying to do is get the X and the Y value, and I'm about to finish those now that I have my picture. So this is 4, cosine is X over R, so 1 over 2. I mean, I wouldn't bother using the R. You don't have to when it's a 1, but if it's anything other than a 1, you have to use it when you're doing definition of cosine. So 4 times 1/2, 2. Okay, I have part of my answer. 2 plus, now I need the Y, and then I'll stick the I on there, and I'll be in full rectangular form. So this Y value is 4 times sine of pi over 3. So using your 5 pi over 3 picture, sine is Y over R. So it's that negative square root of 3 over R. This is negative 4 square roots of 3 over 2. 4 divided by 2 is 2. And then, if you have any double signage, a plus followed by a negative or a negative followed by a positive, either one converts to just a single negative. So in its simplest form, this would be 2 minus 2 square roots of 3 for your final answer. Okay, you're doing the same type of problem here and here, and then here they start you in a different way. They start you in exponential form, but you can still tell what the R and the theta is. That's the R and that's the theta. But when you're in polar form, the R is found out here and the theta is next to the cosine or sine. You can look in either place. The R is out front regardless of what form you're in. Okay, so when you want to find X, just like in problem number 9, you're going to go R times cosine theta. So the R in this case is 7, and then you're doing cosine of the theta that you see right there in the problem, because it's in polar form, you already know the theta. And for your Y value, Now again, the reason that I know I need the x and the y is because of the directions. They want me to give the complex number in this form right here, a plus bi. That's what rectangular form is, when it looks like that. You can't see an r and you can't see a theta, but this is the same thing as x and y, which is why I'm looking for x and y. Okay, the y is r times sine of theta. So 7 times sine of 3 pi over 2, which is the theta they're using in this problem. So try to remember. You might have it memorized, and if not, this is for those of you that don't have it memorized. This is pi over 2, 2 pi over 2, 3 pi over 2. And right when you get here, being that you're on a unit circle, you're at a point that has an x-coordinate of 0 and a y-coordinate of negative 1. This represents the cosine. This represents the sine. So now you can come back and finish this problem. This would be 7, and then your cosine at 3 pi over 2. So this whole thing goes away and you substitute in the value that's equivalent to cosine of 3 pi over 2, which is this x value right here. So when all is said and done, the x value is 0. And then for the y value, it's 7 times negative 1. Okay, so when you go to give your answer in rectangular form, which looks like this, it's the a value, or the x value if you want to call it, plus your y value times I, or in its most simplistic form, negative 7i. Okay, then moving to number 11, I'll do that one just because, there's decimals and everything, and I don't know, I think you get anxious about the problems that have the decimals in it, so I'll do that one as well. Okay, so write the complex number in rectangular form. Again, you got to learn to understand what the directions mean. They want you to give it in this form. That is interchangeable. You can write it like this. Okay, so I'm off to find the x and the y. So this is the third problem. That is just like number 10 and number 9. So the r is that number you see out front, and then times cosine, and there's the theta right there, 7 pi over 10. Remember, when they give you something that's in polar form, you can tell from the format of the problem where there's an r out here and thetas that match right there, that this is the theta and this is the r. That's why I have everything I need. Now, you don't know anything about tenths. So that means this is a calculator problem, which is why they're telling you to round to the nearest thousand. They'll tell you to round to a specific place when they know that it's not a right triangle. So we'll put that in the calculator, and then we're going to go r times sine of theta, which is going to be 0.2 times sine of 7 pi over 10. Okay, so get your calculator. Make sure that you're in a mode of radians, because you're sticking in a radian type number into the calculator. Okay, so for number 11, when you multiply this times this, you get negative 0.118 if you're going to the thousandths place. And you get 0.162, positive 0.162 to the thousandths place when you put that value in there. Okay, so then when you're going to go give your answer, write it the way all complex numbers are written. The real portion first, and then the imaginary portion. All right, so then the only thing that's different about this is that instead of starting you off with polar form as they did in 9, 10, and 11, here they're just starting you off with exponential form. But it doesn't matter, because either one immediately reveals the r value and the theta to you. And that's really all I had in 9, 10, and 11. And then I just tried to memorize that rectangular form of a complex number. It looks like this. And that in finding A and B, I'm really just finding X and Y. This is synonymous to X, this is synonymous to Y. So X is R times cosine theta. I just keep writing the formulas over and over again, so you'll memorize them. But lucky for you, you don't have to memorize them because now you're taking the tests online. So we'll give you a little break in these harsh times. So let's see, the R value is 7, and then we're doing cosine of the theta value that you see there. They have told us to round to 3 decimal places because, again, we can't get exact values for anything other than pi over 4, pi over 3, or pi over 6, or if we're, somewhere right on an axis on the unit circle. Those are the only ones we can do without the calculator. So we'll be putting that in the calculator. And then R times sine of theta would be 7 times this. Okay, again, make sure that you're in radian form. And I believe when you put this one in the calculator, you're going to get 6.657 if you round to the 3 decimal places to the thousandths place. So that's approximately 6.657. And then when you put this one in the calculator, you're going to get 2.163. And then when you put those two things together in this form as they've requested in the directions, it's A plus B, and this shouldn't even be here yet because all you have at this point when you put this in the calculator is the 2.163. This is when you tack on the I, when you give your final answer. Okay, so that's your final answer. Okay, then once you get to 13, 14, 15, I'll do a couple of those. I'm not going to do all 3 of them because they have multi-parts, but I will do one that's in polar form. What you're going to be doing in 13, 14, and 15 is finding a product, and you're also going to be finding a quotient. When you find the product, you'll give the answer in polar form, and you'll also give it in, see, they want it in polar form, the product, and they also want it in exponential form, so I want to work on that with you. Now this one is a little bit easier than the last one I'm going to do, which is number 15, because you can already see the R and the theta. But when I get to 15, they're going to start you off rather than in polar form like this where you can see the R and the theta and jump right into doing the product and the quotient. They're going to give them to you as rectangular numbers. So you're going to have to find the R and the theta yourself and then finally jump into the product and the quotient. So those will be double the work, lucky for you. Okay, so here we go. You need the formulas for how to do a product and how to do a quotient. So I think I'm going to, let's see, where do I have enough room to write this? I can write I might have to do the actual problem on paper, but here's the formulas. So, okay, so actually I need paper to give you this. Hold on next second. Let me see if I can write right here. Okay, so let's say that you have one complex number that's called Z. I'll call one of them Z, Z1, and I'll call the other one Z2. And it's in polar form. These formulas for products and quotients, they only work in polar form. That's why it's nice if they give it to you in polar form. So it'll have its own modulus and its own theta. So everything associated with complex number 1, I'll put a little 1 as a subscript. And then the I term will also have theta 1 associated with it. And then let's say you have some other complex number that has its own modulus and its own theta. Okay, so the formula for doing the product, let's say we're multiplying Z1 times Z2, is just multiply the two moduli, and then with these thetas that you see in here, when doing a product, you add the thetas. So it's the theta from the first complex number added to the theta from the second complex number. And then whatever you get for that sum, that's going to go here as well. Okay, so let's go ahead and do the product, and then I can throw the quotient formula at you. So in this particular problem, let's see, we have the z value. Okay, so let's see if maybe I can fit the product in here. Okay, so the product, we're going to do a product of z times w. We're multiplying the two r values. And then inside here we're going, now they want this in radian form. Type in exact form, use pi as needed. So we're going to keep the angles in pi form. Okay, so when you're doing a product, you multiply the r values and you add the thetas. So this is considered theta 1. The angle that you see appearing here as well as here, that's the theta associated with the first complex number. This is the theta associated with the second complex number. So all you're going to do is add those two thetas, those two different thetas, the 2 pi over 9 and the 1 pi over 9. And that would be 3 pi over 9, which reduces to 1/3, or pi over 3. So therefore, that's what's going to appear back here. Okay, so that answer written a little bit cleaner. I'll write it over, let's see, I'll write it down here. So z times w would just be an 8 out front if you bring that product, to those two factors together in the form of a product. Then after all the simplifying right here, the 2 pi over 9 plus 1 pi over 9 turned out to be pi over 3. So that'll be the angle in the product on the sine as well as on the cosine term as well as the sine term. Both have that pi over 3. And I believe that's as far as they want you to go on your polar form. This is the polar form of your product. We're also going to give this product in exponential form. But as far as the polar form goes, they're going to let you stop there. Okay, so if you wanted to give this answer in exponential form, so all of this goes together and goes in these two spots right here, you would just give this product, but in exponential form. And as we have talked about in all the other problems that we've done in this section, that goes r, the r value times e raised to a power of I times theta. But you're going to be using, the theta that's in the product. So here's your theta times I. And that's the answer that goes there. So you would put this answer right here, right in this blank, and the exponential form right in that blank. Then I'm going to have to move to paper to do the quotient because I've run out of room here. So let me move over to this paper. I'm going to give you the formulas first. Okay, so when you're doing a quotient, let's just talk about these two general complex numbers, and then we'll apply it to the actual numbers that we have in this problem. Instead of multiplying the two moduli, you're going to divide them. The first one will be in the numerator, the second one will be in the denominator. So you're taking z1 and dividing by z2. And then on the cosine and sine information, instead of adding the thetas, theta 1 and theta 2, you're going to go theta 1 minus theta 2. And of course, you're going to get the same difference here as you do here. But I'll go ahead and write it since we don't actually know it as a number yet. Okay, so that's the formula. Now applying it to this particular problem that you have in your outline for number 13. If we do, let's see, what are your complex numbers called? They're not called Z1 and Z2, they're called Z and W. So Z divided by W, we would take the R value that belongs to Z, which is a 2, and then we're going to take the R value that belongs to W. And then inside here where the cosine and the sine terms are, we're going to go the theta that belongs to the Z value, which was the 2 pi over 9. And then we're going to subtract the theta that belongs to the denominator, which was 1 pi over 9. And then your imaginary term with the same answer that you get right here. So 2/9 minus 1/9 is 1/9. Okay, so there is your quotient in polar form. Okay, so you've divided, and this answer is bearing a theta, an R, and also a theta. Now I'll write it a little nicer as you would be writing it in MyMathLab, like reduce that and give a nice clean answer in here. Just one single angle rather than leaving it like that. You want to give both of them like that. Whoops, I left off the word sine here. Like what happened to my sine? Because the sine term always has the imaginary portion either in front or in back of it. It actually doesn't matter, but the books always write it like this. Okay, so that's your quotient. Then what they've been using over and over again here is trying to also get you how to write your answers in complex form. So when you're writing not in complex form, but in exponential form, excuse me. So when you're writing this answer, this quotient in exponential form, and you would just indicate that you're giving a quotient, and then write it in exponential form, which we keep practicing on, is R, the R that you got in the quotient, times E, and then the power on the E, I times theta. And the theta would be right there, the theta that you got in the quotient, times I. So pi over 9 times I. Okay, and then there's your exponential answer. Okay, last problem I'm going to do. 14 is very much like 13, but 15 gives an extra challenge because they're not presenting the complex numbers are not being presented where you can see the theta and the R. You have to make that happen yourself. So let's try and do that one. Here's number 15. I have a little bit of room on the worksheet, so I'll just try to do it right there. I'm going to do some of it up here because these problems have a lot of work, so I need a lot of room for this problem. All right, so let's see. Anyway, you see that this is in A plus BI form, so you don't even have an R. So let's get the R and the theta. You need R's and thetas for both of these. You don't have to write them in, let me see, do they want them in polar form? You can go right into the polar form of the product and the quotient, but to do that, you need R's and thetas. So let's do the R value. associated with this complex number. I'll keep track right down here that I'm doing these things for Z right now. So R is this formula where you use the A and the B value and you square each one. So we've done that in about 80% of the problems in this section have to do with that, other than the vocabulary. That was at the first few problems. All right, so you got 10 squared plus 10 squared, that's 100 plus 100. That means you have 2 times 100 in here. And what you'll do is you'll take the square root of this. It'll come out as the square root, while the 2 will stay inside. So this is the R value associated with this first complex number. You also need a theta. Now first let's talk about where this complex number is. See how it's positive on the front term, the A term, and also positive on the back term? That's like a positive X and a positive Y. You're in quad 1. And since this complex number is in quad 1, the reference angle and the real theta are one and the same. So you can jump right into that. Don't worry about finding it in stages. Okay, this is just Y over X. That's the same thing as B over A. Back number over front number. So this is 10 over 10, which is equal to 1. Okay, so the only time you can get a tan value of 1 is when you are at an angle of 45 degrees, which is equal to pi over 4. Okay, so pi over 4 for the first one. Okay, so this is the theta that's associated with the Z. Now I'm going to try and find the R and the theta. So I got these two values, the R and the theta, but now I'm going to try and find it for W. Okay, so I'll try to put that over here. Let me try and move this out of the way. I'll write it over in the column because I need all the space I can get for this problem. So this one was in quad 1. This one is not in quad 1, so let's talk about where that is. This is like positive X, negative Y. So positive X, negative Y is going to be in quad 4. So I can do the reference angle and then the real theta, or I can just make sure that you stay in the restricted area when you do the inverse. So let's see. First of all, let's do the R value first. Now I'm doing it for the W. So that is front value squared. Make this a little bit longer. So front value squared, and then the coefficient of the I squared. When you square a square root of 3, that's 3. When you square negative 1, that's 1. Some room here. I'm trying to conserve space. So square root of 4 is 2. Okay, so this is my second R value associated with W. Then when I go to do the theta, I'm going to go tan the reference angle. That's Y over X, or B over A. The B is the back value, so negative 1 over the A value. And then let's think about how that picture looks and what the reference angle is. So let's see. I don't know if I have enough space here. And I'll draw it down here. Okay, so I know that I'm supposed to be down here in quadrant 4, because that's where you have signs for this type of number. You know, when it's in, whether it's in rectangular form or polar form, you're still in the same quadrant either way. So positive, negative, you have to be down here. And if I put these numbers on here, Y, this would be X, and then this would be 2. Which we already know. We just found the R value. The R value is really the length of this hypotenuse. But we're trying to figure out where has this thing rotated to, not how long it is. Just putting that, so you'll see that this is short leg, hypotenuse, long leg. This is a short leg, long leg, hypotenuse deal. So across from the short leg is always 30, or also known as pi over 6. Okay, so when you're looking for the angle associated with this, you know, that's the same thing as if you were looking for an inverse. Inverses allow us to find angles. It's just that you're able to do this in your head because you recognize that these are numbers that are associated with a special right triangle. So just remember that, you know, if you want to stay in this restricted area for inverse tangent, you can stay right in here, and you could just rotate down this way so that your theta, because you're trying to figure out how did this arm get here, you could get on right on this hypotenuse by rotating this way negatively pi over 6. So we'll use that for the theta that goes with W. Okay, so we have the R value. We also have that. Okay, so we got two sets of information. We have the stuff for the W, and we have the R and the theta for the Z. Now we can do the product and the quotient, and we can do them in both polar form and complex form because they want these answers in polar and complex form. But you see that these were problems in and of itself to a couple pages ago where we were just trying to go from rectangular form. There was 3 problems that were like this into polar form. Get the polar information, the R and the theta. So now we're going to do this new type of problems, which was numbers 13, 14, and 15, which is to find a product and a quotient. So using these R's and thetas, when we go to do the product, it's multiply the R values, which are 10 square roots of 2 times the other R value, which was 2. And then you go into cosine, and you're going to add the angles. The angles were pi over 4, and you're going to add that to negative pi over 6. And then whatever you get right here, that's going to be the angle on your sine term as well, your imaginary term. So let's wait and see what we get there. And then we'll just put the same angle in there. So let's work on it right here. So let's see, the common denominator would be 12. So you'd have to multiply by 3 and then multiply by 3. So this would be cosine of 3 pi over 12. If you multiply the bottom and the top by 3, you could always do that in your calculator. And if you multiply this by 2 on the top and the bottom, you'll also be in 12ths. And then 3/12 minus 2/12 is 1/12. Okay, so that's the theta that appears in your product. So pi over 12 here as well. Okay, so just writing this cleaner and also in exponential form, we'll go ahead and we'll multiply our 2 R values. So 2 times 10 is 20. With that square root of 2, and then your cosine value has a theta of pi over 12, as well as your imaginary sine term. Okay, so that's the product in polar form. And then in exponential form, okay, then that would be, the product would be written R. That's the 20 square roots of 2. And then in exponential form, it's E raised up to a power of I times theta. And you're using the theta that you already got in the product. So pi over 12 times I as the power on the E. Okay, last thing. Let's see if we have enough room. Here is where we do the quotient. So the quotient, instead of multiplying the r's, you're going to divide them. So the very first r value for z was 10 square roots of 2. And then the r value that went with w was 2. And then when you do your cosine and your sine term, you're going to go the theta associated with z minus the theta associated with w. So the theta that we got for z was pi over 4. And then the theta that we got for w was, so the formula goes the first theta minus the second theta, and the second theta was a negative pi over 6. So yes, we have a double negative going on there. There's always a positive between the cosine term and the sine term. And I'm just going to wait and see what I get when I do this. And I'll put it here instead of doing it all over again. Okay, so this is going to be 3/12. When you multiply the bottom and the top by 3, this is now a plus sign. And when you make this 12s, you're multiplying by 2 and by 2. So that would be 2/12. 3/12 plus 2/12 is 5/12. Okay, so just writing this just a little bit cleaner. 10 divided by 2 is 5 square roots of 2 for the modulus of your quotient. And then it's cosine without all this work around it. Cosine of 5 pi over 12 plus I times sine of 5 pi over 12. And that is your polar form of your quotient. And then finally, giving this same quotient, but in exponential form. That same quotient, I meant to say, I don't know what I just said, that same quotient, but in exponential form would be the r value that you got when you applied the quotient formula, and then the theta that you got when you applied the quotient formula. So it's e, and then you're going to raise that e to a power, and the power is made up of I times theta. This would be the theta multiplied by I. Okay, and that completes section 9.3.